So today we're going to talk about structs and classes, and these are, perhaps the core, sort of core structures of C++ programming language. And you're already seeing a lot of these sort of a way of representing your data. You may have just the primitive types or the fundamental types. You have your integers, Boolean, floating point. Those are very basic, what we call fundamental types built in. And then you may make your own types that are sort of more of a composite. And the way to structure your data in your memory is to use, you can use structs, you can use classes. They are very similar, and we'll see they have some tiny differences. We'll talk about what situation you might use structs or versus classes. So anyway, let's get started with structs, and we're not gonna talk too much about structs because it shares a lot of the features with classes, but still, for historical reasons, we don't necessarily use structs in that way as much, because this is sort of a feature that's inherited from C, and in C++, the structs have a lot more features. It's almost equivalent to classes, but this is kind of a for historical reasons in here that if you want to have compatibility with a C program for whatever reason that in that particular situation, and then you may consider sort of a more of a C style structs. Let's take just a look at a little more details. Now, some people may call structs as a records, which is kind of an old name. Anyway, it's just struct is short for structure. So in C++, you notice a lot of the names are shortened just so that saves some typing when you program. So a struct is it's a collection of fixed number of components or member variables that are actually arranged in memory together. If you have this particular syntax here, essentially have typically one or more variables in a struct, and they are arranged in memory. Actually, if you make an object of a struct type, the values of those variables will be arranged together in memory. They're not going to be scattered around. So here's a somewhat more complex example. You may have a house type, whatever name you want to call it, and then it has style, number of bedrooms, bathrooms, so some properties of the house that you want to it maybe is relevant to your particular problem you're trying to solve. So you may represent a house with this many sort of data points, and yeah, and then the way then you can basically make an object with from that type, you essentially use that type, a house type now is a custom defined type. Use this to declare a new variable. So when you do this, this is basically declared, is not necessarily initialized. There's a rules about initialization. We'll talk about initialization a little bit. This is basically it goes with even with this sort of fundamental types where you have different variables, and then you want to actually before you use it, you should usually initialize them. Otherwise, the variable may be holding some garbage value that it's going to have some unintended consequences. And then, so this is what might look like in memory. So it's sort of, you think of this cells or sort of memory blocks that are going to be arranged in the order you declare them. If your style is the very first variable here, and this will be the sort of the first of this particular object's data area, and then you're going to have all these variables arrange them. So, you know, again, a string is actually, I mean, the thing is this, right? With the string, it would be represented behind the scene. Now, this is an object, right? This might be represented actually behind the scene as a, let's say, a C style char array. And so, but again, this essentially here could be that char array equivalent to, this is an object of that string, and then it holds points to some other location where you have that extra char array somewhere. Before you even have the value for the style, you know, but again, this is sort of tells you it might be equivalent to a sort of a pointer, but it's not really a pointer. And then you have other variables here. So anyway, let me admit somebody that's actually joining with us. Hold on a second. Okay. So to access the member, you use this dot operator, which is the member access operator. There are many member access operators. It's kind of a category of operators. A dot is essentially just one of them. You know, like the arrow, dash, greater than, and that's for the pointer to access that member. And then you may also have the square bracket for an array to access the member. So it's, anyway, the dot is, in this case, you use a dot to access the struct member if you have an object. Now, if this object is actually a pointer, then you would use essentially the, hold on a second. Okay, yeah, if it was a pointer, you use this arrow operator. So in this case, if let's say you have an object, a new student, which is a struct type, right? Then the way to essentially here, what we're doing is we initialize in some of these variables here, and we got the name and we got the GPA, and so this may be arranged in memory like this, and yeah. So once it, you know, you actually given a value, and then they will have a particular length. In this case, you know, your John maybe a 4 bytes. Brown maybe you know 5 bytes, and then you have this coarse grade. So this actually struct gives you a way to arrange your very precisely your memory block, how you want to arrange your data. And so we can also have an assignment. Now, in the case in C++, when you see an assignment, is an operator. Yes, it's kind of fundamental operator. Now, what actually does is that it will invoke, it depends on how you define. Now, by default, if you just have a plain struct, it's going to use the default, it's called copy assignment operator. An operator, we're going to cover operator a little more details actually on Wednesday. And think of an operator as actually more of like a function. You know, you're actually invoking a function behind the scene. And except that you're not really defining this in this case, is implicit, is actually just inserted by the compiler. So that assignment operator is like a function. It takes this argument on the right-hand side and then operates on the object on the left-hand side. And then basically, in this case, it would be a copy. And we'll get to talk about the difference, which is very important in C++, is the copy semantics versus the move semantics. If you have at least heard of that one, we're gonna just look a little more details about that. But in this case, if you have not defined anything, in this case right here, would it be just a copy semantics? Essentially, the content of a new student will be copied into this variable student, which is also a struct. And so again, actually here lays out what actually happens equivalently, behind the scene is every field, every variable of that new student will be copied into student its corresponding variable. And so that's something you kind of be aware of here. So this is a copy semantics. All right. And by the way, so this as I was saying, this you don't really need to write a function that does this, right? Just by the virtue of using this assignment, the compiler already did this work for you, and it will just perform this operation essentially. And if you want to compare structured variables, usually it doesn't make a whole lot of sense to compare two variables of a struct just at a structure level. I mean, you compare sort of different variables, if that makes sense. Let's say you want to check if they are equivalent, if they are equal, sort of in terms of content, right? That equality test, you may, write a function or operator, in fact. Again, so I just a very brief sort of introduction, right? The operator, when you see here, we have this operator, equal operator here. And it's just a very convenient, intuitive way of representing a particular special function. You can also think of this might be just a function called, is it equal, right? And with the take two arguments, right? So that, it's almost like that. It's equivalent. Essentially, behind the scene is like a function, except this is just more intuitive, and then we like this format a little more. So operators are just like functions. And the default operators, by the way, you can override them, right? So we're going to look into those on Wednesday. And right now, we should say these are the default semantics of what this language gives us, but you can actually redefine them. And so here, just talk about how you might just, insert the value of a struct into a data stream, and like you output it into the console. So you can do it like this, right? Now, there is a way to actually, let's say you want to just print out new student, this whole structure without doing this verbose thing every time. Let's say you're doing this many times in a program. Then it might make sense actually for you to override this. Well, it's kind of like overload this operator of this stream insertion operator to handle your new type. Right? So the built-in types are handled. You can see out a string or integer, that kind of stuff. But now you have to define your own type, which is a struct. The language doesn't know how to handle it unless it tells it how to. So then you may implement a function essentially that's gonna define what this streaming insertion operator will do to a new student, object without printing out each field individually. So in that particular function, essentially we'll do something like this. So that's just, we'll look at some code that actually does this for you. And you'll see actually what I mean. So I'm just gonna let you know that is something you can do. And here we may have, okay, this is just a plain a function that does the equivalent, what I was just describing, that we may have a sort of a convenient way just to use this insertion operator as you would, like just a fundamental type. And then you want to have, print out your custom type, then you would have a special function that handles that operator. Now this operator is nothing special, but it's really just like a function that takes the left-hand side of the operator and the right-hand side of the operator, and then does some manipulation. And then in this case, it will actually print a return that same object, C out, so that you will continue, that goes on to the next, the evaluation from left to right. So that's kind of how that works. And Let's look a little, compare struct with an array though. They both can arrange sort of the data elements, together contiguously. But there are some differences. Now, this is actually here is talking about the sort of the default behavior. It doesn't mean like your struct can't do those things. It's just saying, hey, by default, this is what might look like. And so by default, and the arithmetic operations, you don't really operate at the array or struct level. Now, these two types, not all the structs, depends on if you have not defined your custom, let's say, constructors, it's just a plain struct, like the C style struct as an example. So in C, you would declare, just those variables. You're not, adding a bunch of a custom behavior that C++ allows you to do, like you have a custom constructor. If you have that type of struct, those things are actually this array and struct. In that special case of structs are called aggregates. So aggregates, because they're both aggregates, they have this sort of there's certain things you cannot do as an aggregate to, at that level. You have to do it individual element level. Now, the difference between the array when it comes to assignment, you really cannot assign an array to another one. As we previously explained, that an array, the name of the array is almost like a constant pointer. A constant pointer, you cannot modify it. That means you cannot have an assignment of a different value, now the pointer points to a different thing. So that is not allowed. But with a struct, you can. In struct, you have all these elements, that's packaged together. It's a, it's like a status structure, right? It's a structure of bytes together. And then you can actually assign that from one to another that we just saw. The copy assignment operator, that's a default semantics is a copy. But then we'll look at it. There's actually a more efficient way, and there are cases where it's going to save time and increase the performance of the program by using move semantics. We'll look into that a little bit. And then the input output, you can't really just print out an array by just using its name, right? You kind of have to loop through it, right? Similarly, by default, you cannot just print out struct by giving a variable, an object of struct. That it doesn't work by default, as I was mentioning, because the language doesn't understand your custom type. But then you can define that stream insertion operator if you like that, and then you can actually handle that with just almost like a built-in type. And then comparison at the aggregate level does not usually make a lot of sense. You compare the elements or the variables of a struct. Passing parameter. So, we previously said, well, if you can pass an array as a function parameter, that you may, when you pass that name, pass that name around, it does not really do a copy. Essentially, you're just passing that reference around. And then with the structs, you have a choice. You may do a pass by value or by reference. Now, typically, I know the book may have some examples where you may say you pass something, by value, then you modify somehow. Typically, the way we design the program, you don't want to really, modify the parameters that's passed into your function. If you are passing a preference, which is usually, you'll see a lot of this, is because it's a good habit. When you pass a parameter, let's say a struct, you want to usually use a constant reference. So we usually say it's a constant reference. You don't intend to modify the parameters passed in, and it's a reference, so it does not make a copy. And then to return the value of an array, as we previously noted, you cannot just return an array as is, but there's workarounds, right? We can return an object of a standard array, but you can't just return a sort of a C-style array. And then the structs, you can. It's basically like an object, just like a class, object of a class. Now, any questions so far? No? Now, so there, you may have a field, sort of a variable. Sometimes I use this interchangeably, depending on the language. You have what some people call these are the fields of this structure or class. But then these are basically in the C++ language, you more of, they all call them members. You may have member variables, you may have member functions. They're the members of this data type. And so there's nothing special here. We're just saying, of course, you can have a member that's an array. That's, nothing special here. Now, this is telling you, if you actually have this structure like this, and in memory, you might have this thing represented like this. Now, this is actually not entirely accurate here. This length, if it is declared after this array, and it would come, well, actually, sorry, actually this is correct. So if it's declared after the array, it will come after that array in the memory. So essentially that declaration order, it is actually important. There's also, when it comes to initializing the structure, that it will be that order. If you are specializing with a list initialization method with the curly braces, then the order of those variables are going to be important. And so in memory, this is also how it's arranged by that order that you declare. Federico, you lost the Zoom on your open windows. So are you able to hear, or you lost Zoom? What's going on?
Yes, Professor. Don't worry.
You good?
Yeah, I'm good. Thank you.
All right. Well, yeah, hold on. Sometimes when I'm presenting the cursor can get lost also. Anyway, all right, let's move on. And so here, this is just kind of an example of perhaps you're just loading some data into this struct. And you may say, well, I'm going to represent an array and also package that with the length of the array, not the capacity of the array. You may declare the array so I have 100 elements, because an array, you got to have fixed size. Now, you may have this structure that also remembers the actual number of elements that you actually intend to use in that array space. So you may be loading up your array elements like this, starting from 0. The length of the array is 0, and then you give the first element a value, and then now the length has become 1. So you increment that length, and then you assign, then you give a value for this the index 1 element, and then you increment that length again. So this is kind of an example. And you may have seen this in one of our assignments that I have used a sort of a technique like this in one of our early assignments, to have a structure that actually package, an array with its length together. So the actual length of the elements that you're actually using. So thinking of, you may declare an array of a sufficient large size because it needs to have a known size. Thinking is like more of a buffer place. In programming, you actually once in a while you use this. This is very common, but then instead of using a raw buffer, you manage a buffer yourself, and a lot of times there's standard libraries you can use. The reason we use a standard library, if there's something that's available there, you want to use it because they are very well written, well tested, and also you don't want to reinvent the wheel, so to speak. And so this is just an example how you might have, what is the usage of this, having an array in the structure. And then you might see an example here. This is perhaps, let's say, you may have a database of employees, right? Your data, you want to, you may do some accounting, figure out HR stuff, and you have employee records. and they are perhaps persisted in a database. And then when your program is interacting with that database, when you load data back into your program to process data, or maybe you're creating new employee records or manipulating them, and then you may have structures like this that actually does the manipulation, and that represents the data in the program in memory, so that you'll be able to do your data processing. And then as if once it's serialized, this is a structure that you may have that serialized in a particular format that's stored in the database, or maybe you exchanging this data with another program, and then you may consider a certain kind of a data exchange format. Some people may use JSON, some people may use some kind of binary protocol like Google Total Buffer. Some of those things, and when you get to talking about now, you have a program, you want to do some data exchange with programs outside your current program, more of a distributed programming environment. Now, of course, in this course, we don't not really talk too much about the how to really write a program like that, but just kind of give you a little context. These things are very useful, and why do we have these things like this. Now, what you see as struct here, this is really what you're looking at is a C style struct. Now in C++, as I've repeatedly mentioned this, you can really use struct like a class. It has pretty much all the bells and whistles of a class. But for historical reasons, we don't necessarily use it that way. It's just, it's a concept that's in here because of C. And now here, this is essentially declaring an array of employee of that employee type. And so once you have defined a struct with that type, that name is our custom type. And then you use it just like an integer or like some other built-in type. Now you have a custom type that you just defined. And so you just, the rules apply to that new type, just the same way as the other ones. But of course, with this new type, and then you define all the possible meanings or operations you can do on it. And the integer, for example, integer, you can, 1 plus 2, right? And then you may, let's say, doesn't mean it makes a lot of sense. Let's say for employee type, you may also define to say, I want to also have you be able to say employee 1 plus employee 2. Although in this particular case, it doesn't mean anything. But let's say you want to do that, then you can actually, define what that operator plus means. And we'll look at that on Wednesday. So this is just talking about some nested structures. And now within the structure, now you say, hey, it doesn't mean that you can only use the fundamental types or an array. You can use whatever for your member variables. And so that is, including the structures. You may have, within the structure, you use other structures. So there's really nothing to it, and just that you have no limitation, like as to what you can define as a member of a structure. That's pretty much it about structure. It doesn't mean that we have covered everything about structure. It just gives you sort of the typical way we want to use structures for. Although the features of structures can have been expanded to almost equivalent to a class, but we don't really use it that way mostly. And let's take a little code example, and also look at what I meant when I said about some things I mentioned. So here's a little bit of code. Let's say I have a structure. It's called an integer, right? I don't know. Maybe I want to make my own integer, and this is essentially a wrapper around the built-in integer, and that's my value. So essentially, we have a one member variable, and that's called a value. So as I just mentioned about operator, now with my integer, I can define now, because obviously the language is not going to understand what my integer is, right? This is a custom type. So it has defined all the rules and what to do with this built-in int, but for my integer, it doesn't know what to do. So let's say I want to be able to have two integers to be do an addition here, the addition operation, and this is how you might define it. And so as now you see, this is already beyond what you would normally see in a C, right? So this is C++ language. So now we can define functions that actually tell that, sort of encapsulates the operations you can do with this particular data structure. So we're defining this operator with a plus. This is saying, you're defining this plus operator. And so, so here, what we take as a parameter is the right-hand side of that operator. And then this particular integer in the context of this object itself, that's the left-hand side. So here, we're actually creating a new integer, and we don't want to, so basically once you perform this operation, the result becomes a new integer, and the value is initialized. This is the code braces, we're initializing it with a value. So this is a one way of initializing, which is a format you'll see more and more often. And here I'm doing just, instead of using multiple statements, I'm just doing this inside. Doing the operation here, just essentially adding these two values together. This is the sort of the value of this object we're operating on, plus the other value, right? So this is essentially what we're defining what this operator plus will do. And there is another operator here that looks a little interesting. And this operator is essentially defining that if I'm going to convert, this is talking about casting, I can cast this integer object into a string. So this is sort of the type that will be cast into a string. So I just say, well, I'm going to cast this into a string just as if you're going to print out this object, this is what I want you to print out. And so I say, oh, this is my integer type. I have the value. I'll give you what the value is, for debugging purposes, maybe. And then I also define another casting converter that you may cast this into a built-in integer, which is essentially just the value that we're wrapping around. Now, I guess we have explained about, like, explain is the const in the end of this function header here. And that's basically saying we're not modifying this object. Like, we're not modifying this object, like this value here, this member variables, we're not modifying it. So when you declare this as a const function, and you are not modifying, as you'll see inside the function bodies, we are not changing anything of value, right? So that's what it means. That usually, if you're not changing the member variables, you want to have this declared. That's essentially a very strong intention to tell the user of this structure that this does not have a side effect. It's not modifying anything. So here's some sample, just make some, sample operations that you may do. And again, I may have a I1 initialized with a value 10 and I2 I initialize with a value 20. Here you see a format here that's called a designated initializer. I may have multiple member variables, and then I can specify the name. Like maybe I only want to do a partial initialization. Let's say I have 10 of them. I only want to initialize 2 of those 10 member variables. Then you want to, within this particular format, you want to specify the actual variables that you initialize, and by using this dot with the member name, the variable name. I may have another one, all right, and then just make sure that this is in the order of the declaration. And in this here, I may have other variables, make sure that order, as I was saying, the order is significant. And that also goes in here when you initialize the member variables in this particular format. It's called a directed list initialization. So then that's what you can do here. Just kind of showing you different ways of initializing a struct. And here, as you see, I'm using this plus operator, right? Between this I2, I1, and I2. Now this you can do because we have defined the plus operator, what this can do. So essentially, it will just invoke this function. So previously I was saying, when you see an operator, including this stream insertion, it's just a function. It's nothing fancy, right? So we have defined what this plus means. It will do just that. It will actually, after the operation, will return another integer. And that integer will be inserted into that cout stream to print this out. Now, to that integer to be inserted, it does not know. Actually, the compiler will realize, oh, I don't know how to print out, how to actually insert this into this stream, this O stream. Does not really take an integer because it's a custom type. It does not know. We have not defined anything to tell it what to do. And in fact, we'll look at, okay, can I cast it to something that I understand? And in fact, here we'll look through the sort of the converters here, and then we'll actually cast into an integer in this case. And then that's what you will choose by the compiler. But then we'll say, well, I want cast this to a string instead of just printing out a, this integer. This is what it will do implicitly. And now, typically, just a rule of thumb, right? Rule of thumb is try not to do much of the implicit casting. It's a source of bugs because you are not making your intentions clear. And it's more of a code. The code is a form of a communication between programmers when you're programming a team, because your code will be, modified and touched by other people. You want to make your intention clear, even if that's what the implicit rules will do. You want to make it explicit. To make it explicit, in this case, I say, well, even if it's doing integer, I will actually probably want to use a static cast to make that casting explicit. So here I'm just saying, well, let's say I don't like the default behavior. I want to actually print out the string. In this case, it's going to invoke this function here. It will print this out. So, and then let's go through this a bit more. And here is another way of initializing your struct. Now here we'll see this direct list initialization. And this with an assignment here. Now when you see an operator, again, just think about this. You're actually just invoking a function behind the scene. And this function is defined by the compiler. Is a default, by default, it is a copy. It's a copy assignment operator. And the copy assignment operator means that it's going to do a copy. This right-hand side it's going to make a temporary object and then copy the content into your the left-hand side, and that object that you just you're initializing with. So that's just another way of initializing a struct. And now which one to use is a matter of personal style, and it's almost equivalent. So then there's implicit cast. And now here I say it's almost equivalent because we're not defined other types of assignment operators. We may actually say, I don't like to do a copy. Maybe I want to get the last ounce of the performance out of this thing. I may want to just say I want to do a move. And there's a thing you can do with a sort of you can redefine this assignment operator, what it will actually do. Instead of a copy, I want to move it. Because the right-hand side, it's kind of just, it will be abandoned immediately and you have no more use of it. So that is, so here I'm just talking about the default behavior, what this actually will do. And so now here we are, see the right-hand side, we're using this plus operator, I1 plus I2, and then plus I3. When you do this, and by the way, if you hover over this operator, it will show you exactly what function is calling. See, that's the function that we define, right? And then if you assign this to some other type, now this is going to also do an implicit casting because the types don't match. The left-hand side, right-hand, they don't really match. However, we have defined, sort of cast into integer, essentially, what this means. So they will actually support, it will do an implicit cast into an integer to an int, actually, in this case. But again, as I said, typically don't rely on implicit casting, do explicit casting. It's just a safer and avoids bugs down the line. And we can run this thing and to see if, how this runs. And so let's see. Any questions? All right, so let's take a look if this is doing what it's supposed to. This is I1 plus I2, 10 plus 20, 30. And then here we're printing out as a string. So we'll print out this. This is like typically very good for debugging. And then we also have this I4 printed out, which is essentially I2 plus I3, right? 30 plus 30, 60. Okay. Any questions so far?
Not right now, Professor.
Okay, great. Now let's move on to classes. So in this class, we're going to actually introduce a couple of concepts that will be, some of you may be confused with. And I guess some of the concepts are kind of a little advanced, but it's good to understand them. It comes into the inner workings of C++ compiler and the rules of, optimization. But let's look at the basics first, and then we'll look into some of those concepts. Okay. Now the classes are essentially covered. This is what we're going to talk about the content of this, essentially the book of chapters 10 and 11. We have actually introduced the classes in a limited fashion. We talk about the user-defined types, abstract types. It is basically the main thing that allows you to do object-oriented programming, right? And the whole concept of class is essentially that whole encapsulation mechanism. You encapsulate your data and the behavior you can do with that data. And then you can use classes to model the world. Whatever problem you're solving, you think about what are the objects that I'm dealing with. Let's say you have a table, dining table, you have the tablecloth, you have the table itself, you have the dishes on the table, just in the real world. This is kind of a close way of assimilating the world to actually to solve a problem that way, because this is kind of how we're thinking in our mind. And the syntax of declaring classes, now remember, it's just like structs. It's very much similar. Now here, although we are more saying, well, you have a member list. Previously, we're saying you have the variable list, right? But again, as I mentioned, not entirely so, because structs can just, we saw the example, the programming example. You can have a methods, the functions. Sometimes people call it methods. It's just a very different, there's no difference there. So the functions as a member, right, you can do those things, and not just the variables. So they're very much similar, except that keyword here, right? Class, that indicates it's class. And by the way, what we're doing here, we're defining a type. Now we're not declaring any variables here. It's just defining the type itself, and then you use this type name to declare your variables and initialize them whatsoever. So a member is, if the member is a function, right, and then you may declare the function prototype. Now you can declare your member functions within the definition of the class, like the entire body as well, or you may choose to just only declare with the function prototypes, and then you have the implementation of the functions or the function body elsewhere, perhaps in a different file, or maybe in the same file, but outside the declaration, right after the class definition. Either way, it's just a way of organizing your code. If that function is small, usually you can probably just put it inside. There's not much technical difference. In the old days, like earlier version of the C++, there may be a difference, but when it comes to inlining, whether that function is going to be inlined or not. But nowadays, that's no longer a difference there because the compiler will optimize. You don't really necessarily have that much of control on that. So that's not really a main concern, but it's more about how you organize your code. You have seen the example how, in the book or so, we, a lot of times, if it's not just a short example, a lot of times the way you design it, just like in the same, in many of the example you've seen so far, we may have them in separate files. You have a header that only contains the classes with the function prototypes, but not the actual implementation of the functions. And then you may have this implementation in a different file. That's just a matter of organizing your program, your code. And here, as we mentioned, this is only declaring a data type. And there are things about the members. You can set different access level, like they call it access specifiers. When it comes to encapsulating your data and your functions, okay, so those are the things that you can say, well, they are private. If they are private, that means nobody else or no other object outside the class can access the private members, variables or functions, same thing. You may say they are public. Public means they can be accessed by any object outside of it. And protected means they can be only accessed by the derived classes. Like this class is the parent class of a child class. That child can access the protected members of the parent class. In C++, typically we'll say base class versus derived class. In many other language, you'll hear parent versus child. So you can think of that tree structure here. This labels, by the way, a category of class members. You can use them with structs as well. There's, as I said, pretty much everything, actually, practically everything that you can do with the classes, you can do with the structures. It's just that typically for historical reason, we don't really use structures that way. In the UML, we already have covered this. You have seen example, like, let me show you an example. And we have, actually in this repository, there's a number of UML diagrams that you have seen, I guess. This is, for example, you may have UML is just a language that it's useful for object-oriented programming. When you model your objects in your program before you write a single line of code, you want to do some design and then you draw some diagrams. And this is the one type of diagram. It's called a class diagram. You can say, well, I want to know what are the fields, and you do some design like this way, and this is just and this is a particular way to denote. This does not tell you if this is C++ or Java or some other language. It doesn't matter. It's just object-oriented, any language. This is language neutral. So, but again, it's more documentation purpose. So you can use your C++ specific and notations here for your class definition. This is in the early days of UML, and there are tools or vendors that try to generate code from a UML design. They have done that before, but I think it has fallen out of favor. So it's more of a documentation thing. So essentially, then that's a tool for you to communicate and discuss with other programmers, and when you design your program. And so this can be actually rendered. So basically, you say you want to preview this. It will be rendered into something that's a little, it's a diagram or in a picture. And this is the source code. So it just shows you, this is one of those tools that I've recommended you can look into, use. It's called Plant UML. And this is not the only diagram in UML. UML has a couple dozen diagrams for various different purposes. All right. So this is very much similar to structs. Now you have your custom type. I mean, if you just look at this, you don't know if this clock type is a class or struct, could be either. It doesn't really matter. And so when it comes to this declaration of a variable, and when you do this though, it's not just declaring it actually. The default constructor of this class will be invoked. And typically that default constructor probably doesn't do much. And you still want to initialize your data, your member variables. So here's just some example of how it might look in the memory. You have 3 member variables here, hour, minute, a second. And the access and the member access operator, you can use the dot just the same way as the structs. Now, if the members, now this is not just for the variables, for functions as well. If the members are, again, as I mentioned previously, if it's a public, you can access this way outside the class definition, and also the implementation, the function bodies, right? But inside the implementation function bodies, you can access all the members. If it's a private, public, or protected, whatever, obviously you can access those within the definition of the class. But with the object that you declared, then you want to use the object to access the members, and then you basically can only access the members that has the public specifier that you can access. The built-in operations on classes. Now, again, a lot of the operations, you can define them. Now, here we may talk about what the language provides you by default. The language provides you essentially just essentially 2 things, right? You can access the members with this dot operator, or you can do an assignment. And so by default, it will give you the copy assignment operator. So when you do an assign, it does a copy of the object. This shows you what happens if you have an assignment, your clock, assign that to my clock. So your my clock is with this data 2:26:47. After the assignment, the content of your clock is copied over. So now my clock has the same content, but they're not the same object. Class scope. So a class object, obviously you can make that automatic or static. Automatic means you declare that object within a function. And when it goes out of scope, it will be reclaimed. And then if it's a static, that means it will last as long as the program. The lifespan of that object will stay. We'll actually look at an example in a bit how that might be useful. And a member of a class has the same scope as a member of a struct. It's just telling you these 2 things are very much similar. Now, a member of a class is local to the class. That is basically the kind of the core of this whole encapsulation of a concept of a class. Is that so the members are actually local to the class. Now, when you do want to access them, they're not really outside. They kind of gives you a sort of like a namespace. It's a scope. Previously mentioned that you may have like a standard namespace STD. It's similar in that way. That class name gives you that scope, and you may use that scope operator : to access its members when you need to differentiate, maybe because you have the name clash. same names with your local variables, and then you use it that way. But anyway, usually you access the member with the dot operator, but then if you hold on to a pointer, then you use the arrow operator. So objects obviously can be passed around, as a parameters to functions, can also be returned as function values. And most of the program is going to be like this. You're going to have your classes. And maybe it's the standard classes or maybe the ones that you make. So you can pass these objects as a by value or by reference, just same way as a struct. If it's passed by value, and then you're doing a copy. And that copy is essentially when you invoke a function with a class object that's parameter declared to pass by value, you're not using this ampersand as the type. In that case, it will just essentially will do it will invoke the assignment operator, the copy assignment operator to do that as well. It's the same situation as you would just use the assignment operator. So now again, typically we would recommend that you want to pass by reference because it's more efficient. You don't need to make a copy of something, just more time, more space. Passing by reference is more efficient. That's kind of what we're saying. And then the implementation member functions, that's what we already mentioned, that you may put this inside the class definition or outside of it, and even in a different file, if you will. And so it's just a way of organizing your code. When you define it outside of the class definition, though, you have your function, implementation in a different file or outside the class in the same file. So either way, you have to use the scope operator, just almost treating that class name like a namespace, right? Then it's telling the compiler, okay, this function belongs to this class. Now we're defining this function. And in the class, it may have that only prototype, which it declares it. Now you're defining it with a body. So you have to use that. We'll see a couple examples like this, and just some specifics of the language. And here, just another example that when you invoke a member function, what it might do is say, well, I have a set time function, which will actually set the time in the hour, minute, seconds. And then initially, maybe it has no value, and then now you're setting the value. So then you're getting the value into those member variables. So nothing special here, and just an illustration of what might happen. And of course, when you see a function, this function actually will modify the data, the state of the object. In that case, obviously, previously I mentioned the function you may declare as a const function, like constant, in the end of the header. That means you're not modifying this object, but in this case, you are modifying this object. So that means you should not be using that const as the header. And just a couple more examples. And here we are, have somebody else joining. All right. So we have two objects here, and now we have basically a function that's comparing if these two clocks are equal. And then here I have essentially a reference that points to that new object, and that's you're passing this as a parameter, and then in this member function you are referring to other clock as a reference, and then you're operating it Now, as I mentioned before, a reference is really kind of just implemented as with a pointer behind the scenes, but the references are much safer to use and they will be handled automatically. You don't need to dereference it, and with dereferencing is automatic. You can use the dot operator instead of the arrow operator. So there's a couple of differences with the pointers. You know, that is just handled by the language itself. So typically you want to use references as a parameters. It's kind of the main use over there, but that's not the only use. You'll see a lot of the references as the function parameters. So once the class is defined and implemented, and then it can be used, because now you have this custom type. You can use this custom type just like a built-in type. And of course it will follow the rules. What we're talking about, the scoping rules before, and the same thing applies to them. There's really nothing different. You know, now you have a new type, just like an integer. Now you may define the behavior of this type, what you can do. You know, may define certain operations you can do it on it. You know, as previously we were seeing, we have our own integer wrapper. We also define a, you know, what plus means. A plus operator can be operated on your particular type. So essentially, you can implement all, you know, any type that you want in that way. So there's just kind of a way to talk about those member functions. So the ones that you have a const in the end, the ones that you don't have a const in the end. The one with a const in the end means you're not modifying the state of your object or the member variables. In that case, then you can call those functions as accessor functions. Not necessarily super useful. It's just another way that you just want to be aware of. And the mutator function means you're mutating the object in some way. So that's like, it has a side effect. You're invoking that member function, then something about the object changes. Versus the accessor, you're not changing the object. Just kind of know about this concept. It is not terribly useful, but you know. And the ordering, you wonder, okay, I have a public block, private block, protected block, and the ordering of these blocks are not significant at all. And so you can put them in any order you like. Now, constructors. So by default, the compiler is gonna give you some default constructor. If you're not declaring your own, it's gonna provide one for you. And of course, that one will not do much. And it also gives you the copy assignment operator. So when you use the assignment, you're assigning object A to object B. In that case, the assignment operator is already also defined for you, although it may not give you the behavior you want. So sometimes you want to redefine them to actually say what I want to do. So if you have, if you don't have a parameters, that usually we'll call that's the default constructor. The one that you have the class name with an empty bracket. That is called default constructor. If you don't define it, it won't be provided for you. If you do define it and then you have some whatever custom initialization you want to do, then you do it over there. And then you also take parameters of, obviously, you may say, I want to do a partial initialization, or maybe you provide some default values for some of the other member variables, whatever you want to do. So typically with a class, you'll see a bunch of constructors defined. Now the role of the constructor is, of course, essentially just to get the member variables initialized. That's typically what the role is. A constructor actually has no type. It just means that a constructor is a special function. You don't have a direct way of invoking it. It's done, by the compiler to link the specific code block what it actually does. It's not a normal function. It doesn't have a return type. It's just the class name with a parameter list, and then you have a body. Now, of course, you can have more than one constructor. Typically, you'll see a lot of them have a bunch of them. Maybe you want to give different flavors to allow the user of the class to be able to initialize their objects in different ways, just as a convenience. So constructors are invoked when the object is essentially when it's declared or initialized. And then when the class object goes out of scope, it actually will invoke another special function that's called a destructor. The destructor is the class name with a tilde in front of it. That's the particular format. Whatever the language defines, not that important, but this will be invoked automatically. This is we've seen this before, so basically that's where we do the cleanup. If you have a pointer, that's where you probably want to delete it to avoid a memory leak. That's where you want to just release the resources that you have hold on to. So when you see a statement like this, right, you're declaring an object here, a variable. It's going to invoke the default constructor because you're not provided a sort of argument list. So this is a little different from, let's say you have you declare an integer a, right? That is declared now. So the rules of the language has evolved somewhat. It's, you know, the language spec still says is initialized. You know, in the old days we say, hey, that's not initialized, you're only declaring it. It is still initialized, just that it's initialized to a random value. The value is indeterminate. It's that's basically what that means. But then it may, if you want to use that value, you want to do a summation of something, you want to initialize it to a 0, for example. Typically, you want to 0 it out. Otherwise, you're going to get a surprising result. But then in the case of a class, that initialization is done differently. Here it's going to invoke a default constructor, whether you provide it or not, right? If you don't provide it, a default one will be provided for you by the compiler. So that just give you a more concrete example of the clock type we've seen before. So of course, you can also invoke specifically, explicitly invoke a particular constructor. You have a constructor that takes some parameters and then say, you're making a new object of this class with these arguments, and it will invoke the corresponding constructor. It will match the one that you know you have used here. You know, so the compiler will actually go look for the corresponding constructor. A constructor can also have default parameters. That just allows you to collapse multiple versions of constructors into one. You know, because you want to provide default values for a certain number of variables, and default values, just like what we've seen before in the default function, is the same thing. A constructor is just another special type of function. You can have default parameters with the, you know, for the parameter, you can say equal, you know, 0, right? Equal empty string. So you can have those things. So as we said before, if you don't provide a default constructor, the default constructor will be provided for you. And then this is say member initialization class declarations. This is, so it's talking about, we're going to see an example in a bit. So essentially, when you, within the constructor, right, you can initialize your member variables with the initialization list. If I can probably just show you a little bit of code, let's see if I have something here. Okay, right here. So, well, this is a little, perhaps it's a little more complicated example than, but again, just look at the format, not the specific inheritance. Now, I guess this is something we're reviewing for those folks that you already know. but we're gonna get to that base class in a bit. This is just saying, with a constructor, you can initialize your member variables. Now, this is not exactly initializing your member variable here, but initializing the member variable your base class. But the concept is the same. You can have a list of here. Let's say, imagine if you have actually a member variable. Let's say you have a member variable of, int n, right? Let's say, and then you may be initializing them in addition to the base class, but you have to, then you can say I'm initializing M, N, and B like this. So you can have a list of a member initialization in that manner. You don't need, instead of using assignment in the constructor body, so you can use that way. That's just, again, this is mentioning something about a new feature, but again, anything in the standard, that's what you should know. The language evolves. Okay. So this is telling you if you declare an array of class objects, then you should have a default constructor, because that's the that's the only way the program can actually initialize you an array. You just have to have a default one, even though your object may not be fully initialized, and maybe you may have another for loop to initialize your elements. So the destructor we already mentioned, this is when the object goes out of scope, the destructor will be invoked. This is kind of the very last thing it will do before it will actually release the memory of that object. And so this gives you a chance to do some cleanup, like releasing a pointer. So that's what destructor is for. So this is just a specific, format. It's just like a constructor. It's another special type of function you define in a class with a tilde in front of it. It does not have a return type. It's like a function, but it's really not like a normal function. But it just functions. It's like the same. It serves the same role as a function, but it's a special type of function that's telling what the compiler can do. All right. So now this part we have already talked about ADT, and so we're not going to repeat on that. Now just talk about a little bit about between structs and the classes. I've already kind of explained how you might pick one versus the other. Functionally, they are equivalent, except the default. Now the intention of struct is that the members of the structs are public by default. That's kind of the intention, although you can make them private, but it's rarely you want to use it that way. But in classes, if you don't use the specifier, the public or protected or private, by default, they're going to be private because by design, they're meant for you to hide the information. The member variables are not to be manipulated by the program outside the class. You can only access the member variables through the functions that define. So you have a very defined way to interact with the state of the object. So that's kind of their intention, although they are functionally equivalent. So the inline functions, as previously mentioned, if you define, you have the function body within the class definition. In the past, it's called inlining. Although there's a keyword inline you can use, but it doesn't really mean so much anymore. The compiler is going to do its optimization whether you have the keyword or not. Even if you define the function outside of the class definition, it may still be inlined by the compiler. So this particular part doesn't really matter too much anymore. Now, the classes can actually have not just those members that we previously saw. Those are, their life, the life span of the member variables. It goes together with the object itself. When the object goes out of scope, it will invoke your destructor, which you may or may not define, but either way, and the data that's held by your member variables, they're all going to be released together as part of the object. So that is the lifespan of that. But then once in a while you say, well, I want to have a variable that's part of the class. I say, well, I want this thing to live beyond the lifespan of the object or any object that you declare or define for this with this class. So that static member serves that purpose. That's not just for the member variables. You can have a static, but you can also have a static functions. A static function usually is some kind of a utility. It does not matter what the state of the object is, because it does not operate on a particular object. But you know, it will. You can use that to modify the state of an object you're passing as parameters, but there's no this object anymore within the static member, a static function. So you're not really having the context of this object you're operating on. That's with a static function. So in fact, let's just take a peek at an example. Any questions so far?
No, Professor.
All right, good. Well, I will go over this a little bit, but just kind of show you what it might look like. You may have a static function as a member of the class. You may also have static member variables. Okay, so not talking about specifics of the example, I'm just going to show you what it might look like. This, you may have this. You have a public section, you have public members, you have a protected members, you have a private members. Okay. And the static members of a class, what does that mean? So, you know, for the non-static member, now when you don't have the static keyword here, if you remove the static keyword, that means this is a non-static. I mean, for lack of a better word, really, it's like static or non-static. So this variable is non-static. And then if you use a static keyword, that's called static. The static, this word itself is kind of overused, honestly. This keyword can mean different things. But you know, we're talking about this class context. This is what it means here. The static member of the class are shared by all the objects of the class. So when you see these member variables, that means they can be accessed by any object in this class. You have whatever object that you're using throughout your program. These static members, there's only one copy of it. There's only one copy of that static member, and it can be accessed by all the objects of this class. So that's kind of the key property of a static member variable. And the static function is basically means that you can access the function without, it's not within the context of this class. Basically, you don't need an object to use this, although you could access this function on an object, but you can also access this function without using the object, just basically by using the, let me give you an example, by using the class name. See, this instance function is a static function. The way to access it, you just essentially use that class name as a scope with a scope operator, and this is how you access a static function. It's not tied to a specific object, so you don't have an object. Use the dot member access a specifier that was seen before operator with a dot. You don't need to do that. But although if you have an object, you can still use the dot to access it, but it's not necessarily recommended. Typically, you want to use this format. It also signifies to the reader of your code you're accessing a static function. Okay. Now, the whole OOP design, object orientation, is, you know, the key feature of that is once you have various different classes now, they're not just random things, have no correlation, they have relationships. And, like a car has an engine, or let's say a rat is a mammal, right? You may have a class that's mammal, describes what this mammal can do, has, variables and functions. And then you have things that's specific to that rat, what the rat will look like and what it can do, which is also a mammal. So that is describing a is a relationship. We're saying this rat is a mammal. That's called, once you have these two classes, you have the rat class, you have the mammal class. So the rat class is a mammal. Essentially, that's inheritance. And so the rat class inherits all the features of mammal. So whatever the mammal can do, all the things this rat can also do just by this association, it is a mammal. So that's inheritance. Composition. Now, there are, unless the relationship sort of is we're modeling the real world. That's kind of what the object orientation gives us, that OO design. This is how we think of the world, so that's why we can think naturally. So that's why it's so popular. We want to use this way, and then you can program without object orientation, obviously, like a C. But it is popular because this is how we think of the world. It's easy to model the problems, and typically we say unless the relationship is a relationship, the inheritance is very apparent. Usually in terms of the resiliency of your program, just a good program design, that you want to use composition as much as you can. Composition means that like a car has an engine, a car has wheels, right? Then essentially you're declaring those objects, your wheels, your engines of your car object as member variables, right? So instead of inheriting all the features of wheels, I mean, it just, your car is not really a wheel. Your car is not an engine. It has an engine. It has wheels. So those are the member variables of your car class. And so the way you model that is that way. So typically that's preferred because it allows you to refactor a code much more easily. And then when you have the inheritance, it's just your code is more rigid. So unless that relationship is very apparent, then you do that, but otherwise composition is just, remember that relationship is usually better, more flexible. And this is just some examples here. So here, as I was saying, in some languages they call parent class, child class, or this is the kind of, or you have this whole chain of inheritance. And then you have, just thinking in terms of family tree, right? That's an analogy here. In C++, a lot of times we mostly say you have a base classes and you have derived classes. The base class is the one that, like a mammal is a base class, and then your rat class is derived class for a mammal. And now something is a little special here about C++ is that it allows you to inherit from multiple base classes. And do I have an example here? Okay, I might not have an example here, but the thing is, the real world example, well, the thing is, the typically what you want to do though, this is not unusual. So you want multiple inheritance. In some language, they say, well, you actually have a class that implements many interfaces. That interfaces describes certain features or traits of your class. But in terms of like a concrete class as actual parent, you normally want to limit that to one. Instead of having multiple, you have a sort of a diamond shape of inheritance, which will have ambiguity. And it's just not very natural if you have that kind of situation. So, but what you can do is have those things called interfaces here, but instead of it's called virtual classes. The virtual classes, they should have at least one virtual function. Virtual function means that that class, the base class, does not have that function implemented. It's just, it has a declaration with a virtual keyword in front of it. And then, you know, the derived classes will implement that. Let's say, you know, let's say the mammal class, you want to declare that as a virtual. Let's say, you know, you have a function that says it can, so let's just say it has a name. So the very basic thing has a name. That name, you can declare it as a virtual function in that base class, and then your derived class will implement it or pass it on. You know, if it's not implemented, by the way, if your function, your derived class has not implemented, it has any function that's not implemented, you cannot instantiate, you cannot really create an object out of it because you have a certain behavior not defined yet. So unless you complete that chain of inheritance, you have all the virtual functions defined, and then you can do that. So here's an example, actually. This is, so you have a shape that defines the very basic properties of a shape. And then you have circles, you have rectangles, and then you have squares that are actually rectangles, right? It's just that the two sides are the same. And this is a class diagram. You know, see those things, the boxes are empty there because we're not listing the actual field, the variable, member variables and function. The members you are defining here, you actually want to put them in a lot of detail, but here we're only interested in the class relationships. So we're just omitting the members of the classes. And this particular arrow in UML language, it is the is a relationship that defines an inheritance. So it shows you clearly what this means. This is a tool for communication. Right? When you do a design of your problem, and you say, okay, I want to have these classes defined, and I'm gonna then, you know, say these, I want to have these classes. Then I'm gonna define, okay, what are the properties or the member variables that I want to have for each of those classes. Then you kind of, you know, you make your program that way. So this is general syntax. You have have not mentioned here about the member access specifier. So you have seen this example here. I thought I had, let's see, class access specifiers. Okay, so here, so take an example, right? So we have again, as I mentioned, the functionally structs and the classes are pretty much equivalent. So here, let's just have a struct B, and then this is a virtual function that I mentioned. Essentially use a virtual keyword. Now, if you're gonna put a equal to 0, means this is a pure virtual function. Now, pure virtual function means this, you do not intend to implement this in this for this structure or class. By the way, the structs, classes, and unions, they are called class types. So they're all categorized as the class types. They are basically have the, you know, a lot of the features are the same. So, you know, then you have a derived class D, and here we're going to override. So we're going to implement this function f that's declared as a virtual in the base class, and then here, so we have this actually defined. So now you can instantiate D, create an object out of it. And then the thing you want to see here is this member access specifier. This can be public, protected, and private. And private is default. Now, what does this mean, right? So what does this actually mean here? So when you are inheriting from a base class, this access specifier, this actually defines how do you want to treat the public methods or public variables, basically the public members of a B. How do you want to treat them from this class D? If you make an object out of D, you know, what's the visibility of the public members of a B? What this means. So when you say public, that means the public members of a B are going to be public in D as well, right? So if you make an object of D, all the public members of a B will remain public. This is what it means. If you say, if you remove it, and by default, it's going to be private again. So we mentioned the difference between struct and class is that default behavior. By default, for a class, things are private. by default for struct things are public. That's just the intention of those things. There's this tiny little difference there. So if I say you know, again, I don't say don't provide this keyword is kind of an optional, then that means it's private. The public members of B are private. Or if I say you know, protected means the public members are become protected. Protected means they can only be accessed by the derived classes. The children or the grandchildren can access it, right? But not from outside of the class. So when you declare an object, you cannot use use the dot operator on it. You cannot access those members anymore. So this is defining how do you want to expose the public members of your base class. That's what it is. Any questions? Okay. So redefining or overriding, the more common term is called overriding member functions of the base class. And here we see an example of overriding. And this keyword is optional, by the way. You don't have to have it, but it's good and happy to have it if you're actually overriding a base function that it's a communication, it's documentation purposes, right? So you do want to just use this keyword when you're overriding. So we have a rectangle type, right? Let's say rectangle is you have a length and a width. You have a bunch of functions. What you can do with the length and the width as a part of a rectangle. And let's say you also have a box type that is a rectangle type, right? So this is a relationship. You're defining that inheritance. So essentially when it comes to code, it means that you have the rectangle type right here as a base class after the colon. And the box type, now you define box type, but what box type means, I have one more dimension, I have the height. So then you have a bunch of new functions that, you know, operate with this specific box that's not available in a generic rectangle. I'm not saying it's very practical in your reality. This is a demonstration purposes, what you can do here. And then you'll see that set dimension is actually not really overridden because actually it's a different method. It has a different parameter list. But the area, for example, that might be overridden if you redefine it. And if you don't redefine it, then well, the same method will be inherited, available in box type. Okay, constructors. So we have seen an example of constructing your derived class versus your base class. See where that is. Constructors. So here I have a class A, and then the class A says, well, class A doesn't have a default constructor, by the way. It has a so once you define a constructor with a parameter or more, then the one with the empty parameter, the default constructor, it's disabled. You know, you basically that's the way it is. So once you define it with the parameters, then the one without is not valid. And so if you have a base class, a derived class that inherits from A, you have to initialize your base class object. So because that is required, now you have a one specified custom constructor, then you have to initialize that. Otherwise, your object construction is not complete. So you gotta do that. So that's what here you see. This is in the member initializing list, and so you need to initialize your base class. This is kind of shows you when it comes to constructor, the responsibility of your derived class in the construction. You have to initialize your base one, even if, let's say, even if you don't take any parameters here for your B, you still gotta initialize your A. That's, you know, because that is required because it doesn't have a default constructor anymore. Okay. Now, destructor, the only thing you need to know about destructor is that, okay, in the construction process, when you, let's say, make an object of a B, it's what it will happen is the member variables of A, if it has any, will be initialized first, and then it comes to B's, new variables will be initialized. And that's in that process. It goes from the base to the derived. When you doing the cleanup, destructor, which is the opposite order. So in the initialization, you initialize the base and then derived, and then in destruction, you basically destruct the B first and then A. So it's like, think of it as almost like a stack. You're pushing element into the stack and then you're popping them out, last in, first out. So the header files, we'll kind of cover that. Essentially, that's how you organize your code. Now, I do want to mention one thing that you probably have seen this a lot already, is that there's this thing called include guards. So the include guards, so previously we have a bunch of those examples. Let's see if I can find them. So this one, so anything starts with a hash symbol here, like typically these things you see, hash include, hash if not define, and define. These are called directives to the preprocessor. So in your compilation, you're building your program, one of the step, before it compiles, there's a pre-processing step. The pre-processing step, this is the instructor to tell the preprocessor what you want to do. So that include is also a preprocessor, directive to actually, to say what's called the translation unit, how it does the compilation, put the code together from what file, it will arrange your code accordingly. And now what typically you'll notice that is because that include mechanism is that you may have that include in multiple different places and you don't want to have the code duplicated. So you want to have this thing called a include a guard. Here, you want to just have some kind of unique string here. So if that symbol is not defined, then you define it. So the next time you include the same file, this symbol is already defined. It will not include again because this will become false. So that's what it is. It's the include guard to allow you to include your file, your header files typically without duplication. Now there's another way to do it. This is the standard way of doing it, is defining the standard. There's another way is non-standard. Although it's not standard, it is supported in most major compilers. It's called a pragma once. So you see an example here. The pragma once is just an alternative way. So instead of saying not define, and then you have end if, right? You basically have 3 lines. And then what you can do is essentially you have just the 1 line says pragma once. And so that's a special instruction to the preprocessor for the compilers that actually support it. Unfortunately, this is not standardized, but if you are targeting, only specific compilers, essentially all the major compilers, they support it. So this is safe to use, although it's not standard, okay? This is saying a derived class cannot directly access the private members of its base class. Yes, so private means private. Private means the derived class cannot access private members, but the protected is what allows the derived class to access it. So you have full control over what members you want other objects to access or other classes. So this we have covered, the inheritance. All right. Now there's a couple of special topics now. So far, any questions? What's covered so far?
No, right now.
Good. Okay. There are a couple of important topics actually that is not in the text, and It's actually very important to know because actually some of those features are relatively new. I guess it's because the text is a little out of date. It doesn't necessarily explain those things. Okay, so let me just go through some of those things. Okay, first thing is the value categories. The value categories are, if you read C++ standard documentation, various different parts of documentation is going to always talk about the value categories. And if you don't understand them, you're going to have a hard time reading the documentation, the official documentation. It gets complicated and you don't understand what they're talking about. So in C++, you know, most things when it comes to statements, most things there are expressions. So when it comes to like sort of compilation process, those expressions, like, so here are examples of expressions, right? So this is a statement, this is an expression, and now even this whole expression on the right hand side is an expression, left hand side is another expression, okay? And this whole thing is an expression itself. So there are expressions. When it comes to expressions, there are, if for the expression to actually indicate values, there are different value categories. So when an expression has two things, it has a type, and then it has a value category. So now it's the best to explain in examples. Now, forget about the middle level. This is just a little tree here. Just shows you the relationships. Expression. You can have a GL value. It's called a generalized L value and R value. Okay. Now L value, R value. Now where does this name come from? It came from historical reasons. Nowadays they actually have different meanings. The historical reasons, when you see a statement like this, the left-hand side is, and previously it's called L value for left. And then the right-hand side of that assignment is called R value, right value, right-hand side. And that's where it came. But the concepts, they have changed since. And so in fact, for every value, there's only one of three categories. It's either an L value, X value, or PR value. PR value is called a pure R value. So L value, is better understood as a locator value. What does it mean? So locator value means that this value has a location in memory. And also it means that it has an identity, what we call identity. So like I has a location in memory. Why? Because you declare it right here. And now, as the previous I said, when you do this, it does not mean it's not initialized. It is initialized. So you declare this variable, it's also initialized. Initialized to what? It's not a 0. It's whatever name, whatever value in that random memory cell it is right now. It's a free memory. Okay, the memory obviously used by various different programs without running of your computer. It has whatever values in there is junk. It's a garbage value in there. So it's initialized as a garbage value. So, but this I is an identifier. It has a location in memory. So you can actually print out that location, right? You can use the ampersand and ampersand I, it will give you the location. You can print it out actually. So it has a location. So I over here in this expression is an L value. Then the 7 here, it's called a PR value. PR value is a pure R value. Now PR value, what are they? Now PR value does not have a location in memory. It's just a value. And now that value during the program execution, it might be put into register, running the machine code, but this value is not allocated in your memory, or I can't say definitively, but then it even if it has a location, it's not a location you can access in your program. I guess put it that way. Okay, the compiler may do a bunch of things behind the scenes, but it is not something you can access. It's just it doesn't have a location. Some cases it may have a temporary location, but just for the purpose of understanding the concepts, it does not have a location for you, right? So 7 here is not, you have no way of referencing a location in memory for 7, right? That's a PR value. X value, we'll look at some examples of X value, but most important thing, understand these two things first. So in this expression, I equal to 7, you have an L value on the left. Now, you can assign a PR value to L value, but you cannot assign L value to a PR value. This won't make sense. This is an example saying this won't make sense because 7 here as a PR value does not have a location. It cannot hold a value. You cannot assign something to something that doesn't have a location in memory. So that's what it means. And then here, likewise, this expression here, even though J is an L value, right? Now, J is an L value, it has a location. However, you do a multiplication with a 4, this expression, when you do this L value will be evaluated, okay? If let's just say let's assume J has a value, okay, whatever the current random value is, okay? The garbage value, it will have some kind of value. This will be evaluated because this operation here, as this expression, it'll be evaluated into a number. It may have a temporary location, but this is not something you can access, right? Let's say compiler needs to do a temporary, but this is also a PR value. So just kind of help you understand, this expression is also a PR value, it's not an L value. So a PR value, you cannot assign something to that PR value. It has no location, at least not one you can access. So that's why this is also invalid, okay? You still following so far?
Yes, it's all right, Professor.
All right, now pointer. You have a pointer P. The pointer P dereferenced pointer. Now when you dereference a pointer, the dereference pointer gives you an L value, okay? Just, these are the rules that the language defines. You kind of, we're getting into the rules for the compiler. If you're writing the compiler code for C++, this obviously is what you have to, this is what the compiler code is going to do, and the rules in the compiler. Now, we need to understand some of those rules, so it helps us understand the documentation of the standard library. It's going to mention those things like this. So the reference pointer is an L value. It gives the location, right? The P points to a memory location, and you dereference it. This gives you an L value, and that's ready to receive a value, basically, right? You don't assign a value to P. P's content is an address, but if you dereference it, it becomes the actual location. There is an L value, can receive a value. So you can do an assignment. This is okay. Okay. And now I here, now remember, I was L value, right? It is okay to assign an L value to an L value. Now, L value, when you assign to an L value, this will be evaluated. When it's evaluated, it becomes a value 7, and that 7 is a PR value. So that's kind of how it works. Just kind of explaining some examples here. Now here, this might look a little strange, right? This looks strange. Have you ever written code like this? Probably not a whole lot, right? But this is valid. Now, why is it valid? Now, some preconditions. The I and the J has to be the same type. So this is a optional operator, right? A conditional operator, sorry, conditional ternary conditional operator. Some languages they call it Elvis operator. I don't know why they call it Elvis operator, but anyway. Depends on the value of I, is going to evaluate this expression. This will end up giving you either I or J. Now we know I or J, they are both L values. So the end result of this is going to give you either I or J. So it's an L value. And the L value, you can put it on the left-hand side of the assignment operator. It can receive a value. So this is valid. Okay. This is an L value. The end result of this is an L value. All right. So in the one more example here. Now the constant, so we have seen this constant keyword used in various different places. A constant means non-modifiable. So you have a variable that's not modifiable. And this not modifiable value, obviously you cannot have an assignment to it, right? So it's still an L value, right? This has a memory location, but you cannot assign another value to it because it is a constant. The only place where you can do an assignment is at the place where you declare it. And then once you declare it as a constant, it cannot be modified afterwards. All right, just some introduction with these things. When we see some examples of X value, I'll point it out, but this is really the main thing you wanna know. And then the other thing is, I've been talking about the move semantics. So by default, the compiler is going to give you a copy assignment operator. So when you do the equal, you assign an object to your object, a class, and that by default, the default behavior is going to do a copy of that object. And you may not want to do that. Let's say, because, let's say for performance reasons. In the standard library, you're going to see a lot of this, the move semantics that's you'll see used in different places. And I want to just help you understand a little bit what that means. So now again, remember when you see struct in the classes, they are functionally equivalent. Now the difference is like if I see a struct with this function like here, not function, this is a constructor. Actually, if I define a member variables or member functions, they're all going to be public by default unless I use the access specifier with a colon, right? And then you can modify it, but you don't really use that way with a struct typically. But anyway, so this is just a simple example. You have a struct W, X, and this is the constructor. I have a constructor. I don't even have a name here because it doesn't really matter. We're not using parameters, so this is okay. And this is a reference. You've seen this, right? So we're passing by reference. If you construct a W, object of W, you pass two integers, and this is going to use a reference. Now, here's a problem. Because it's using reference, right? You can't really do this, right? Let's just say, you can't really say, I want to have a value, a W, say W1, and a 1 and 2. You can't do this. Why? I see that the compiler one right now, the IDE shows you an example, error, right? Well, actually, it's the error. This is sometimes the compiler may not give you the error that makes sense, but what's really happening is this. 1 and 2, they are PR values. They don't have a location in memory. If they don't have a location in memory, you can't have a reference to it. Reference means you pass by location. There's no location to it. You can't do this. All right. So we have X and Y. Now X and Y, the difference is we have the consts. Sometimes you want to give different flavors of constructors sometimes. So it just shows you have a constant references that you're not modifying the passed in parameters. Now, we're going to talk more about the template, but again, you'll notice actually we have to look at some templates, but it's nothing mysterious, okay? It's just you have more arguments to your, in this case, you have a function. The template, you can make various different functions that has different types that is extracted out as a parameter to the template. So I have these types of A1, A2, and T. It returns a pointer to T. So there's a new thing maybe you've seen, you don't understand what it means. It's unfortunate is using this overloaded, overused ampersand. Ampersand means a lot of things, as you notice in C++. If you use ampersand in front of a variable, is meaning it's an address of that variable, right? If you use it as a parameter here, right, you're passing by reference. Now you use double ampersand here as a parameter. This is the, it's called the R value reference. Now we have understood what R value is, right? Like 7 here is an R value. This is R value reference. Means that it's okay if you pass that 7. It will take 7. It's still going to be passing by reference. It's just, it's a little weird, but you know, 7 is probably not a great example, but let's say you make an object. Let's say you make an object of W. I'm going to see an example right here, actually. Okay, not an example here. The example is something different. But anyway, so the 7 is fine. That's is R value, so we don't have a location. It's a PR value, but this is a reference to it, and so you actually, if it's a PR value, it will take it. If it's actually a X value, well, we're actually going to see an X value is not in here. Now, if it's if it's actually a L value, it also works too. So essentially, by doing this, as you notice, we can actually take different types of parameters. This forward actually just means that we're going to pass that reference forward to another function call. So if it came in as a R value, if it came in as an R value reference, it will continue to be R value reference. But otherwise, it will convert if it's an R value, it will convert to an R value reference. So essentially, it will give you an R value reference. And then this T type is parameterized. So it's just kind of, when you really end up using it, it just kind of show you that, remember that W, X, Y, Z, right? They are, you know, they use references, right? And so normally you would not be able to initialize a Z directly with a 2 and 2, right? Also, you cannot initialize X with a 2 and B either, because B is not a constant. So if you look at X, well, actually A is not constant. It needs a constant for the first argument. So anyway, this allows you, with this factory, this particular template function here, it allows you to initialize those objects of W, X, Y, Z with a single function, right? This function, because this declared as R value reference, allows it to take an L value as L value, or R value, PR value, or PR value is also R value, they both would work. And then not only this, it's passing in, it's calling the constructor. This new operator, right? We're actually just calling the constructor of this type, WXYZ. Think of the T as WXYZ, right? We are generalizing it. We're passing 2 arguments here. So these things will forward the reference to those constructors. They're going to continue to receive reference. Those reference arguments will work. Even if I pass in a 7 or 2 and 2, it's going to make an R value reference out of it so that it will work with the constructor where it needs a net reference. Normally, it will not work if you just directly initialize z with the 2 and 2. All right. Now, another example here that I show is that because that this is going to show you what standard library where you see the string. It's also and this plus operator is a concatenation, and that concatenation actually uses the all value reference. You see that? Just you need to understand this all value reference so that you can actually read some of the standard library. Otherwise, you probably have a trouble understanding what this actually means. So the left-hand side is using the all value reference, and by the way, yeah, because using that, it will you will be able to actually pass in. You will be actually pass in the you know, constants that actually doesn't have an address, or in this case, think about this. This string, you're making a new string with a initialized with age. This expression here, it does not have an address. It may have a temporary address, right? This is not identified. You don't have this assigned to a variable, okay? It's part of that larger expression. So by using the all value reference, you're able to capture that and still pass it on as a reference. So that location is not accessible normally. You can capture it this way with all value reference. So you can, you know, you're not doing a copy, for example. But if you don't have this, you know, all value reference, if I just using the L value reference, the ampersand, if you're single ampersand, that's the L value reference. The single ampersand, that means it requires location is an L value reference. This reference needs to point to, you need to pass an L value to it, essentially. And here, we don't have an L value. This is an all value here. So this is why this works. This is how the library implements it. So this is another important feature of C++. Question about this all value reference? So we are running out of time, and we're gonna leave some other features for Wednesday. On Wednesday, we're gonna also talk about templates and overloading with the operators. We have already seen some of these things through the discussion of the current lecture and previous lectures, but we're gonna look into a little more detail. Today, for today's content, we have introduced a lot of stuff. I want you guys to spend the time to digest. So there won't be an assignment for today. You know, I put in a bunch of examples. Actually, the programming examples I put in the code is in the book, and you know, perhaps you can go through them, see if you understand them, and it just kind of gives us a little more, a little exercise that will give you a little more picture of what you can do with the classes. They may not have some of the advanced features that I'm talking about here, but once in a while, I'll bring in some of those things. And then if you actually look at a CPP reference.com, that is kind of the sort of the standard documentation for the language. A lot of the when you look up something here, and then let's say, you know, you're gonna see some of those, you know, unusual features. You kind of have to have some basic understanding to be able to read them. So I hope that's going to be helpful to you. Any questions so far?
Okay, thank you.
Yeah, if not, this is pretty much it for today. And I use this time. I don't want to burden you with more assignments. I just want you to really spend time. If you haven't finished your other assignment, you can continue to do that assignment. But for today's lecture, I want you to just look at the code, you know, the example, the juice machine and grade report, and then read the book, just to digest this a little bit, okay?
Okay.
All right, I'll see you guys on Wednesday.
Okay, Professor. Thank you.
All right, bye-bye.
Oh, have you already stopped the recording?
Not yet, hold on. All right, yeah, stop the